So we have Physics Ph.D. qualifying exam practice problem number 30 in domain of quantum mechanics. So let's begin. Consider two interacting identical fermions in one dimension with the following Hamiltonian: H equals negative h bar squared over 2m. Quantity second partial with respect to x of 1 plus second partial derivative with respect to x of 2. Plus 1 half m omega squared x of 1 squared plus x of 2 squared plus g delta x of 1 minus x of 2, where g is greater than 0. Part A, transform to center of mass and relative coordinates. So this is a variational principle and many body systems problem. So for part A, center of mass and relative coordinates, capital R equals x of 1 plus x of 2 over 2. Lowercase r equals x of 1 minus x of 2. X of 1 equals r, capital R plus lowercase r over 2. And x of 2 equals capital R minus r over 2. The Hamiltonian separates as h equals h sub cm plus h sub rel, where h sub cm equals negative h bar squared over 4m, second partial with respect to r, plus m omega squared capital R squared, or second partial of capital R. And here h sub rel equals negative h bar squared over m. This second partial here, this second partial derivative here with respect to r, plus 1/4 m omega squared lowercase r squared plus g delta r. So the reduced mass is mu equals m over 2. And h sub rel equals negative h bar squared over 2 mu. Derivative with respect to r, second derivative with respect to r, plus 1/2 mu omega squared r squared plus g delta of r. Okay, part B, construct an antisymmetric trial wave function satisfying exchange symmetry. So here, antisymmetric trial wave function. So for identical spin polarized fermions, the spatial wave function must satisfy that following: that capital psi x1 comma x of 2 equals negative capital psi of x of 2 comma x of 1. And since exchanging particles sends r to negative r, the relative wave function must be odd. Okay, so that psi sub relative negative r equals negative psi sub relative r. And a natural trial state is the exact non-interacting fermionic ground state here. So that capital psi t x of 1 x of 2 equals 1 over the square root of 2. And then we have this Slater determinant here in this first row. We have that phi naught x of 1, phi sub 1, x sub 1, second row, phi sub 0 x of 2, phi sub 1 x of 2. So here that phi, that phi naught and phi sub 1 are the first two one-dimensional harmonic oscillator orbitals in the center of mass and relative coordinates. This is proportional to the following. Okay, so we have that capital psi sub t capital R comma lowercase r is equal to the following. Okay, and we have the center of mass ground oscillator state. Phi sub 1 r is the first odd relative oscillator state, and here that's phi, some would say phi sub 1 of 0 equals 0. And so here we have capital psi That's sub t x comma x equals 0. Okay. All right, so that's B. Part C, using the variational principle, estimate the ground state energy. So let's see if this holds. We'll just, sorry about that. Okay, so variational ground state energy here. Let me just put this in focus. Okay, so variational ground state energy, the variational estimate is here for this E sub t, where we have bra psi t, h ket psi t, divided by bra psi t, ket psi t here. And since the Hamiltonian separates E sub t equals E sub cm plus E sub rel, we could say the center of mass oscillator has mass m equals 2m, and the frequency omega. So E sub cm equals 1/2 h bar omega. And the relative oscillator has reduced mass mu equals m over 2, and the same frequency omega. The odd relative ground state is the n equals 1 harmonic oscillator state. So E sub rel equals 3/2 h bar omega. And the interaction term contributes that expectation value here, G, delta R, that equals G, absolute value of phi sub 1 of 0 squared, and that equals 0. And that's because the odd relative wave function vanishes at R equals 0. So we could say E sub t equals 1/2 h bar omega plus 3/2 h bar omega, so that equals 2 h bar omega. And this is not just variational for spin polarized identical fermions. The delta interaction has no effect on the odd relative sector, so E naught equals 2 h bar omega. All right, and for part D, determine how the result changes in the strong coupling limit. So for the strong coupling limit for identical spin polarized fermions here, you have this capital psi x sub 1 equals 0. So delta x sub 1 minus x sub 2, capital psi x sub 1 comma x sub 2, that equals 0. So the interaction term does not shift the energy even as G approaches 0. So we get the following for that E naught G approaching infinity equals 2 h bar omega. And for two distinguishable particles or two fermions in a spin singlet state, the spatial wave function could be symmetric. Then the delta repulsion would matter strongly, and in the G approaching infinity limit, the system would fermionize, approaching the same energy 2 h bar omega. However, for already spin polarized fermions, the result is already 2 h bar omega for G is greater than 0. All right, and for part E, we want to discuss the physical meaning of the Pauli exclusion principle in this system. Okay, so for part E, the physical meaning of Pauli exclusion, the Pauli exclusion principle requires the total two fermion wave function to be antisymmetric under the exchange. Capital psi 1 comma 2 equals negative capital psi 2 comma 1. And for spin polarized fermions, the spin part is symmetric, so the spatial part must be antisymmetric. So that capital psi x sub 1 comma x sub 2 equals negative capital psi x sub 2 comma x sub 1. And so we could say capital psi of x comma x equals 0. Physically, two identical spin polarized fermions cannot occupy the same one particle spatial state. In the harmonic trap, the lowest energy arrangement places one particle in n equals 0 and the other in n equals 1. And giving E equals 1/2, giving E equals 1/2 h bar omega plus 3/2 h bar omega, that equals 2 h bar omega. The Pauli principle arrangement places one particle in n equals 0 and the other in n equals 1. I'm sorry, I read that. Let me just backtrack here to make sure that I read this properly from here because I just got sidetracked. My apologies. Right here, physically, two identical spin polarized fermions cannot occupy the same one particle spatial state. In the harmonic trap, the lowest energy arrangement places one particle in n equals 0 and the other in n equals 1, thus giving E equals 1/2 h bar omega plus 3/2 h bar omega equals 2 h bar omega. The Pauli principle creates an effective avoidance between the particles even without an explicit interaction. And we could say E naught is going to equal 2 h bar omega for two identical spin polarized fermions in the harmonic trap with contact repulsion. Okay, so my apologies for mispronouncing anything. Thank you very much and have a great day.